Hi, I'm Luis Kirsch, and we investigate general purpose in-context learning. This is joint work with James, Jasha, and Luke. We are interested in general purpose meta-learning. This is the idea of driving advancements in machine learning using meta-learning. That means we want to discover novel general purpose learning algorithms that are reusable across a wide range of tasks. In this paper, we want to put as few inductive biases in the model and learning algorithm as possible. We do this by using memory-based or in-context learning to learn. What is an in-context learning algorithm? In supervised learning, you can think of it as a function which takes as an input an entire dataset of inputs xi and outputs yi, and a query point xtick, which maps it to its prediction ytick. Of course, not all functions in this form are learning algorithms. The subset that corresponds to learning improves their predictions ytick the larger the dataset D is. The next step then is to represent these functions using neural networks, such as LSTMs or transformers. Here we use our general purpose in-context learning transformer, gpickle. How do we find transformers that don't just directly solve the supervised problem, but implement learning algorithms? Our hypothesis is that we need many diverse tasks. With sufficiently many, we expect to discover general purpose in-context learning. So how do we obtain these tasks? We generate them. In our particular case, we start with a base dataset, like MNIST, and then we generate many more tasks by linearly projecting the images. Each task has a specific randomly drawn linear projection and a specific randomly drawn labeled permutation, which forms a new dataset D. We create n of such tasks and then meta-train our transformer in a multitask fashion across all of them using only a single prediction head. But under what conditions does learning to learn emerge? We train many models with various numbers of tasks and model sizes and plot their final accuracy after training. First, we do so with an MLP, which does not take the entire dataset as an input, but just the images xtick and produces labels ytick. The higher the capacity of the network, the more of these tasks it can fit. In comparison, our transformer takes in a sequence of data points from the same task that our query xtick is from. At a certain model size and number of tasks, we observe a phase transition where we seemingly can fit an unbounded number of tasks. And as we will show, this is when the transformer starts to learn how to learn. Beyond this transition, the model also generalizes to unseen tasks in this area. But do we actually observe learning to learn here, or is it merely zero-shot generalization? To investigate that, we looked at how the performance changes as a function of the number of examples seen. The longer the sequence, the more examples the transformer sees, the higher its accuracy gets. So it looks like a learning process with within-sequence improvement. It also generalizes. We can metatest the model trained on MNIST on fashion MNIST, and vice versa. We have observed a phase transition in the number of tasks and model size. Now we look at this more closely. We plot the within-sequence improvement between the first and last example on the y-axis, increasing the number of tasks. In the first phase, there is no improvement on any task within the sequence. This just corresponds to instance memorization. When further increasing the number of tasks, we go into the next phase, which is task memorization. This within-sequence improvement only happens for seen tasks. Finally, with more tasks, there's a very rapid phase transition to quite general learning to learn, where we generalize to unseen tasks and even unseen datasets. Our transformer thus exhibits three different phases in terms of meta-learned behavior. The literature on neural network scaling laws already identified the number of parameters as a crucial ingredient for performance. Surprisingly, across several different architectures, when performing meta-training, we observed that the parameter count does not predict the performance of the last prediction all too well. Instead, the large state size is most crucial. The state size can be seen as the memory, like the hidden state of an LSTM, or the number of activations in a transformer. It more strongly predicts the performance of the architecture as a general-purpose learning algorithm. If you're excited about research on general-purpose meta-learning, reach out and meet us at the poster session.